Scientists have discovered the largest known stars in the universe, located roughly 19,000 light-years away. Stephenson 218 is a red supergiant, possibly an extreme red supergiant. Found in the constellation Scutum, it lies toward the inner region of the Milky Way, inside a massive star cluster called Stephenson 2, also known as the RSG C2, discovered in 1990 by astronomer Charles Bruce Stephenson during an infrared survey. This cluster is essentially a graveyard of massive stars. It also contains at least 20 to 25 red supergiants, which are stars that have exhausted their core hydrogen and expanded to enormous sizes. For decades, we believed that stars like UY Scuti or VY Canis Majoris represented the maximum size a star could reach. But that assumption is now being challenged. As we leave our solar system, that significance begins to fade. In the vast emptiness between stars, our sun quickly becomes an invisible point of light. To reach the Scutum Centaurus arm, we must cross the interstellar void, heading towards a region where the density of stars and gas increases dramatically. It is here within the RSGC2 cluster that we find a stellar giant that pushes the limits of how large a star can be. The Stephenson 2 cluster is not a typical neighborhood. It is located at the intersection of the Scutum crux spinal arm and the galactic bulge, a high-traffic area for star formation. This cluster is unique because it represents a population surge of massive stars. Most stars in the universe are small, long-lived red dwarfs, but here, around 20 to 25 stars have reached the red supergiant phase at roughly the same time. To understand the scale of the Stephenson 218, we have to look at its predecessor, UY Scuti. For years, UY Scuti was the benchmark, measured at roughly 1,700 solar radii. However, as our measurement techniques improved, moving from simple visual estimates to high-precision infrared parallax, the data shifted. We realized that the upper limit for a star's physical size is much more flexible than once thought. Stephenson 218 isn't just a record holder. It is an outlier that pushes the limits of the Hayashi limit, the theoretical boundary that dictates how large a hydrostatic star can be without losing its stability. To grasp the magnitude of this star, we have to visualize the journey through our own neighborhood. Imagine rushing past Saturn. Its rings are thousands of miles wide, but only about 30 feet thick, appearing like a razor-thin disk of ice. Beyond Saturn lies the dark outer reaches, but if Stephenson 218 were our sun, we would be inside the star. New measurements and refined infrared data have confirmed that Stephenson 218 is estimated to be around 2,000 times the sun's radius. To process this, consider this volume. It would engulf the orbits of Mercury, Venus, Earth, and Mars. It would swallow the entire asteroid belt. It would continue expanding past the orbit of Jupiter and extend close to the orbit of Saturn. If you were to fly a commercial airplane around its surface at 500 miles per hour, the trip would take you 1,100 years. Even light traveling at 300,000 kilometers per second would roughly take around 8 to 9 hours to travel around the star's circumference. This isn't just a large object. It is a celestial environment, so vast that its surface gravity is incredibly weak, despite its massive volume. This low gravity is exactly why the star is fluffy, allowing its atmosphere to extend billions of miles into space. We didn't find this star by looking through a backyard telescope. It is buried between thick curtains of galactic dust. To see it, we must look at the sub-millimeter spectrum using the Atacama Large Millimeter/Sub-Millimeter Array, ALMA, in Chile. Recently, astronomers Mark Siebert and his colleagues from the Chalmers University of Technology use ALMA to observe the RSGC2 cluster. They focused on a sibling star, Stephenson 2 DFK52. What they found was a ghost of a star's past, a colossal cloud of gas and dust being expelled into the void. By utilizing Doppler spectroscopy, the team measured the velocity of this material. The data revealed a massive nebula spanning 1.4 light-years across. In astronomy, we use the terms blue shift and red shift to describe movement. Blue-shifted signatures show gas rushing toward the Earth. Red-shifted signatures showed material moving away. The data showed that roughly 4,000 years ago, the star underwent an episode of extreme mass shedding. It didn't just leak solar wind. It threw off 5% to 10% of its total mass in a singular, violent event. This reveals that the death of the red supergiant isn't a single explosion, but a series of catastrophic purges that begin 1,000 years before the final collapse. Why are these titans so unstable? The answer lies in the battle between radiation pressure and gravity. In a star like our Sun, these forces are in equilibrium. But in a monster like Stephenson 218, the core is producing so much energy, the outward radiation pressure nearly overcomes the star's own gravity. There are two primary theories for this extreme instability. Binary interaction. Most massive stars are not alone. There may be a smaller, companion star orbiting deep within the giant's outer layers, acting like a cosmic whisk that stirs up plasma and helps eject it into space. The Eddington limit. The star may be reaching a point where its luminosity is so high that the outer layers are essentially blown off by its own light. If you genuinely enjoy exploring the universe and its mysteries, consider subscribing. It helps us keep going. If you could stand on a moon of Uranus and watch a sunset with Stephenson 218 at the center of our system, the view would be terrifying. The star wouldn't be a sun in the sky. It would be the sky. The horizon would be a flat wall of red plasma, a reminder of the universe's indifference. The cosmos don't care about our concepts of up or down. It only cares about the distribution of mass. We must face the reality that Stephenson 218 is a temporary titan. In the realm of stellar evolution, it is a live fast, die young object, while our sun is a steady candle that will burn for 10 billion years. Stephenson 218 is a forest fire. The star is currently burning through its remaining fuel at an accelerated rate. Once the core attempts to fuse iron, it will lose its internal pressure support in less than a second. The core will collapse, triggering a Type II supernova. For a brief few weeks, this single star could briefly rival the brightness of the entire Milky Way galaxy. It will then leave behind either a neutron star, or more likely, a stellar mass black hole, a tiny, invisible puncture in the fabric of space-time, replacing the largest star ever found. The mission to map these monsters is far from over. Astronomers are now turning the James Webb Space Telescope, JWST, towards the RSGC-2 cluster. Webb's MIRI, mid-infrared instrument, can peer through the dust clouds, 10 times the resolution of previous telescopes, potentially revealing the hidden companions causing this mass shedding. We are also awaiting the next data release from the Gaia spacecraft. Gaia is currently mapping the positions and velocities of over 1 billion stars. A slight adjustment in our parallax distance from Stephenson 218 could change our size estimates significantly. If the star is even 1,000 light-years further away than we think, its calculated diameter would increase, potentially pushing it toward 2,500 solar radii. We are 8 billion hearts on a tiny blue dot, trying to make sense of a universe that operates on a scale we weren't evolved to understand. Stephenson 218 is a reminder that there is always something bigger, always something more mysterious, and always a limit to what we think is possible. If we found a star larger than this, one that could swallow Neptune, what would that do to our understanding of the laws of physics? Is there a final boss of stars out there, hidden in the dark, waiting to be found? Tell me in the comments what you think the absolute limit of a star's size could be.